In this lesson, we will delve into Task 1.4 of Project 1, which involves the principles of milling and the application of two systems, specifically focusing on the milling cutter clamping system and dynamic balancing technology. The clamping system of a milling cutter is like providing a home for the cutter, and its quality directly affects the cutter's operational state. Meanwhile, dynamic balancing technology is crucial for ensuring that the milling cutter can operate stably and efficiently at high speeds. Next, let's explore these two aspects in detail. In milling operations, the milling cutter clamping system and dynamic balancing technology are critical components. They play a significant role in enhancing machining precision, extending tool life, and ensuring the stability of the machining process. Milling cutter clamping system. The primary function of the milling cutter clamping system is to securely mount the milling cutter onto the machine spindle, ensuring that the cutter is accurately positioned and operates stably during the machining process. Common milling cutter clamping methods. 1. Spring collet clamping. The spring collet is a commonly used clamping method that utilizes the elastic deformation of a spring to secure the milling cutter. Its working principle involves the collet being compressed by axial force when the collet nut is tightened, thereby clamping the milling cutter. The advantages of this clamping method include its simple structure and low cost, making it suitable for milling cutters with small to medium diameters. For example, spring collets are often used to clamp milling cutters with diameters ranging from 6 to 20 mm on some small CNC milling machines. Hydraulic chuck clamping. The hydraulic chuck uses the pressure of hydraulic oil to clamp the milling cutter. Inside the chuck is a hydraulic chamber, and when hydraulic oil is injected into this chamber through an external hydraulic device, the pressure of the oil causes the inner wall of the chuck to deform uniformly, thereby clamping the milling cutter. The advantages of the hydraulic chuck include its strong clamping force and high concentricity, which ensure high precision machining of the milling cutter. Hydraulic chucks are widely used in precision milling operations, such as the machining of aerospace components. 3. Heat shrink chuck clamping. The heat shrink chuck utilizes the principle of thermal expansion and contraction to clamp the milling cutter. During installation, a heating device is used to heat the chuck, causing the inner bore to expand. The milling cutter is then inserted into the chuck, and as the chuck cools, the inner bore contracts, tightly gripping the cutter. The advantages of the heat shrink chuck include high clamping precision and good rigidity, allowing it to withstand significant cutting forces. In high-speed milling operations, the heat shrink chuck is an ideal clamping method. Precision requirements of the milling cutter clamping system. The precision of the milling cutter clamping system directly affects the machining accuracy of the cutter. Concentricity is a particularly important metric in this regard. Concentricity refers to the degree of alignment between the axis of the milling cutter and the axis of the machine spindle. Poor concentricity can cause eccentricity during rotation, leading to issues such as chatter marks on the machine surface and reduced dimensional accuracy. Generally, for precision milling operations, the concentricity error should be controlled within a few micrometers. For instance, when machining high-precision molds, the concentricity error needs to be controlled within plus or minus 3 micrometers. Dynamic balancing technology. In milling operations, the milling cutter typically needs to rotate at high speeds. If the mass distribution of the cutter is uneven, it will generate unbalanced forces during rotation, leading to vibration and noise, which can affect machining accuracy and tool life. Dynamic balancing technology involves adjusting the mass distribution of the milling cutter to reduce the unbalanced forces generated during rotation to within permissible limits. Generation of unbalanced forces. Unbalanced forces are primarily caused by factors such as geometric shape errors of the milling cutter, uneven material density, and manufacturing processes. For example, uneven grinding of the cutter edges or the presence of pores within the cutter body can lead to an uneven mass distribution of the milling cutter. When the milling cutter rotates, these unbalanced masses generate a centrifugal force, which can be calculated using the following formula: F equals m times omega squared times r, where F is the centrifugal force, m is the unbalanced mass, k, omega is the angular velocity of the milling cutter radians per second, and r is the distance from the unbalanced mass to the center of rotation, m. From the formula, it is evident that the centrifugal force is proportional to the square of the angular velocity. Therefore, as the rotational speed of the milling cutter increases, the unbalanced force increases dramatically. Classification of dynamic balancing. 1. Static balancing. Static balancing refers to aligning the center of gravity of the milling cutter with the axis of rotation while in a stationary state. This method is typically suitable for milling cutters with lower rotational speeds and smaller length to diameter ratios. The process involves placing the milling cutter on a static balancing stand, allowing it to rotate freely. When the cutter stops rotating, the heavier side will be at the bottom. To achieve static balance, balance weights can be added to the lighter side, or material can be removed from the heavier side, ensuring the center of gravity is aligned with the axis of rotation. 2. Dynamic balancing. Dynamic balancing refers to achieving equilibrium of both the inertial forces and the inertial couple moments of the milling cutter while it is in a rotating state. This method is suitable for milling cutters that operate at high rotational speeds. Dynamic balancing requires the use of specialized dynamic balancing equipment for measurement and adjustment. A dynamic balancing instrument can measure the amount and angle of imbalance of the milling cutter during rotation. Based on the measurement results, material is added or removed at specific locations on the cutter to achieve dynamic balance. The importance of dynamic balancing. In precision milling operations, dynamic balancing technology is particularly important. For instance, in the aerospace industry, the machining accuracy requirements for components are extremely high. If there is imbalance in the milling cutter during high-speed rotation, it can lead to microscopic chatter marks on the machined surface, affecting the surface quality and performance of the components. Moreover, an unbalanced cutter will exert additional impact forces on the machine spindle, accelerating spindle wear and reducing the machine's service life. Therefore, in precision milling operations, it is essential to perform strict dynamic balancing on the milling cutter to ensure machining quality and the normal operation of the machine. The spirit of craftsmanship in pursuit of excellence, from the high precision requirements of the milling cutter clamping system and the strict control of dynamic balancing technology, we can deeply appreciate the spirit of craftsmanship in pursuit of excellence. In precision milling operations, there are almost stringent demands for the dynamic balance and clamping accuracy of the tool system. Even the slightest error can lead to a decline in machining quality, affecting the performance and the reliability of the product. This requires us to be meticulous with technical details in our actual work, striving for ultimate excellence. Whether in choosing the milling cutter clamping method or performing dynamic balance adjustments, we must hold ourselves to the highest standards, continuously improving our technical skills and professional competence to ensure that every machined product achieves the best quality possible. In this lesson, we primarily study the milling cutter clamping system and the dynamic balancing technology. Regarding the milling cutter clamping system, we learned about common clamping methods such as spring collets, hydraulic chucks, and thermal shrink chucks, as well as the precision requirements of the clamping system, particularly the importance of concentricity. In terms of dynamic balancing technology, we covered the causes of imbalance forces, the classification of static and dynamic balancing, and the importance of dynamic balancing. Through the study of this knowledge, we have also deeply appreciated the significant role of the spirit of craftsmanship in precision milling operations. I hope that in your future studies and work, you can apply this knowledge in practice, continuously enhancing your professional skills and vocational competence.